The Milky Way is on a collision course with Andromeda. It's not a story, it's physics. Our galaxy and this neighbor are going to merge. It's already set in motion. And by the end, you'll see the whole arc of it, from that first pull of gravity all the way to the quiet shape of a new, single galaxy, a super galaxy. This is a dance that takes billions of years, and we'll look at what it means for our solar system. Right in the middle of it, we'll face the fact that the night sky will change. It will become something we wouldn't recognize. It makes you wonder, if even galaxies aren't permanent, what is? Our galaxy is a spiral of stardust, so huge it's hard to even picture. We live inside it, out on one of its arms, and we call it the Milky Way. From here, on a dark night, you see it as this pale, shimmering band across the sky. It's a pinwheel of hundreds of billions of stars, and our sun is just one of them, all of it held together by gravity and by dark matter spinning in this slow dance. It takes our solar system about 250 million years to go around once. But our galaxy isn't alone out here. There's another one, its great rival, waiting in the constellation Andromeda. If you look on a really dark night, you can just see it, a faint, fuzzy smudge. That's the most distant thing you can see with just your eyes. That's the Andromeda galaxy. It's a spiral too, and it's even bigger than ours. Through a telescope, you see its true shape, a tilted disk with over 1 trillion stars. A bright core, and these sweeping arms lined with blue star clusters and pink gas clouds. It's the biggest galaxy in our local group, and it has its own little satellite galaxies around it, just like the Milky Way has the Magellanic Clouds, those irregular blobs you can see from the southern hemisphere. For most of history, we didn't know what these smudges were. We thought they were just clouds within our own galaxy. That changed less than 100 years ago with astronomers like Edwin Hubble. He used a big telescope, the Hooker telescope, and he found special stars inside Andromeda, Cepheid variable stars. Their pulsing light told him how far away they were. And the distance was staggering. Andromeda wasn't inside our galaxy. It was millions of light years away, an island universe all its own. That one discovery changed everything. It showed us the true, empty scale of space between galaxies. So now we know, these two great spirals are the main ones in our little corner of the cosmos. Two giants slowly circling each other in the gravity well they share. And if you start to see them as characters with their own size, their own mass, their own structure, then their future isn't just a prediction. It becomes the first chapter of a story. For a long time, that faint smudge in Andromeda was just a mystery. Even when telescopes got better and you could see its spiral shape, the thinking was settled. It had to be a nebula, a cloud inside our own galaxy. The idea of other galaxies was too radical. The establishment held onto that. Then there was this astronomer, Vesto Slipher, working at Lowell Observatory. He wasn't just using a telescope, he used a spectroscope which splits light into a rainbow. Every element leaves a fingerprint in that rainbow, a pattern of dark lines. In 1912, he pointed it at Andromeda, and he saw something. All those fingerprints were there, but they were in the wrong place. Every single one had shifted slightly toward the blue. That shift is the key. It's the Doppler effect. You hear it with a siren. When an ambulance comes toward you, the sound waves compress, the pitch goes up. When it moves away, the waves stretch, the pitch goes down. Light does the same thing. A light source moving toward us has its waves bunched up. That's a blue shift. Moving away, the waves stretch. That's a redshift. Slipher measured a blue shift for Andromeda. So it was coming toward us, and he calculated the speed. Hundreds of thousands of miles per hour, much faster than anything inside our galaxy. That was the first real evidence. Andromeda wasn't just a static cloud. It was a massive object moving, headed roughly our way, but there was still a puzzle. How far away was it? If it was close, that motion might not mean much. If it was very far, then the speed meant something else entirely. Edwin Hubble solved that. Using the big Hooker telescope, he found special stars in Andromeda, Cepheid variables. They pulse, and their pulse rate tells you their true brightness. You compare that to how dim they look from here, and you get the distance. The number was huge. Nearly 1 million light-years away, far outside the Milky Way. It was its own island universe, a separate galaxy, so you put the two discoveries together. Liffer's velocity showed it was moving toward us. Hubble's distance proved it was another galaxy. The implication started to sink in. These two huge islands of stars, with all that empty space between them, were on a path that would eventually bring them together. It was a correction. We weren't the center. We were just part of a slow dance that had already started. That discovery changed where we saw ourselves in the universe. But it left a bigger question. Why is this happening? The answer is a force we know so well we hardly think about it. Gravity. It started with an apple. Isaac Newton saw it fall and understood the same force was holding the moon in its path around Earth. He gave us the math for attraction. How every piece of mass pulls on every other piece. But gravity isn't just a pull. Centuries later, Albert Einstein saw it differently. He said mass warps space and time around it. Imagine a heavy bowling ball on a stretched rubber sheet. It makes a deep dip. Now roll a marble near it. The marble isn't pulled by a string. It just follows the curve of the sheet, spiraling down toward the bowling ball. That's gravity. It's the shape of the universe. Now look at our part of space. The Milky Way and Andromeda aren't alone. They're the two biggest in a small cluster, the local group, with dozens of smaller galaxies. All of them are tied together in a web of these curves, like marbles on that same sheet, each making its own dip, all linked in a slow dance. The Milky Way and Andromeda are the heaviest marbles. Their dips are so deep they're pulling each other closer. There's no cosmic friction out there, no air in the vacuum of space to slow it down. Once they're on this path, their fate is set by the basic rules of physics. You can picture it like two strong magnets on a perfectly smooth, endless table. At first, nothing happens. They just sit there, but their fields are already connected across the gap. If you wait, you'll see one twitch just slightly and start to slide. Slow at first, then with more speed, accelerating across that frictionless surface until they meet with a clack. That's the path of our galaxies. Cosmologists are clear on this. It's not a chance meeting, it's a certainty. The early measurements of their motion and mass have been checked for decades. The math is clear. In the emptiness between galaxies, nothing breaks gravity's bond. We are in the long, quiet slide before the final embrace. The scale of time is it's hard to hold in your mind. We think in decades, centuries maybe, but the galaxies, their story is told in billions of years. To even start to see it, you can take the whole age of the universe and squeeze it into one calendar year. The Big Bang, that's midnight on January 1st. Our solar system doesn't show up until early September. The dinosaurs, they're walking around on Christmas Day. And everything we call human history, from the very first cities to right now, all of that fits into the last few seconds before midnight on December 31st. So where does the collision with Andromeda happen? That's an event for the deep future of this cosmic year, long after where we are now. It's not a tomorrow. It's not a next year, it's an epoch. The latest measurements from Hubble, from Gaia, they say the first close encounter starts in about 4.5 billion years. 4.5 billion. When the first single-celled life was starting in Earth's oceans, this event was already set. It was a certainty. When all the continents were still one landmass, these galaxies were already drifting toward each other. That's cosmic time. That's the normal, patient rhythm of how galaxies evolve. Stars are born and die over millions of years. Galaxies rotate over hundreds of millions. A merger like this, it's the slowest ballet, the grandest one. To put it on a timeline we can almost get, you look backward and forward from where we are. Our planet formed about 4.5 billion years ago, so the journey to this galactic encounter, it's equal to the entire lifespan of Earth. The age of the dinosaurs lasted about 180 million years. In this context, that's a blink. The whole history of our human species is less than a footnote. This perspective, it doesn't make our story small. It frames it inside a narrative of almost unimaginable patience. We're living in the quiet, early chapters of a saga. The climax is so distant that our own sun will have changed long before the final act. That stretching of time, it's essential. It prepares you to see it, not as a sudden crash, but as a drawn-out, graceful, inevitable rearrangement of two entire worlds of stars. 4.5 billion years from now, the dance actually starts. Andromeda's not a smudge anymore. It's this huge, tilted disk that takes up the whole night sky. The two galaxies make their first close pass. They don't collide head-on. They swing by each other like a slow pirouette, but their gravity is so strong, and that's where things start to get messy. You have to think of a galaxy not as a solid thing, but as all these stars and gas and dust held together by gravity. When Andromeda gets close, its gravity pulls on the far side of the Milky Way harder than the near side. That difference in pull is a tidal force. We see that with the moon and the ocean tides. Now imagine that force on a whole galaxy. The Milky Way's spiral arms, those elegant curves, they start to stretch like pulling taffy. The neat pinwheel structure warps. And the same thing is happening to Andromeda. Its shape is getting twisted by our gravity. So for the first time in billions of years, these two ordered systems begin to lose their shape. They get warped and messy long before they actually merge. What happens to the stars inside? The key is that space is mostly empty. The distances between stars are enormous. Our sun's closest neighbor is over 4 light-years away. That's trillions of miles of nothing. So when the galaxies swing past, the stars themselves are like grains of sand in a huge, empty stadium. They almost never collide, they just slide past each other, their paths bent by gravity, but the gas and dust between the stars, that's different. Those clouds are huge and diffuse. They don't slide past neatly, they slam together, they get compressed, and when you compress giant gas clouds, you trigger something. This first pass will likely ignite waves of new star formation across both galaxies. Vast stellar nurseries light up, creating clusters of hot, young blue stars. The night sky from any planet inside would become this chaotic canvas of new suns being born, even as the old spiral patterns are torn apart. It's a preview, a violent, beautiful opening act where creation and destruction are part of the same song. Our galaxy has a supermassive black hole at its center. Sagittarius, a star, 4 million times the mass of our Sun. Andromeda has one too, even bigger, over 100 million solar masses. Right now, they're each at the heart of their own galaxy. But as the galaxies merge, these black holes will start to move. They'll be pulled toward the new, combined center of gravity. They'll begin to orbit each other. A slow, tightening orbit over millions of years, and their huge mass warps space and time around them. As they spiral in, they send out ripples, gravitational waves. We've detected these from smaller black holes. LIGO has. The merger of our galactic cores will create the strongest signal, a low hum across the universe. Their final merger will be catastrophic in its energy, a huge pulse of gravitational waves, more energy than all the stars shining at once. But on the scale of the galaxy, it will be quiet. The stars are too far apart. No solar systems are thrown out. The structure holds. It shows how empty space really is. The most violent event, right at the center, just settles the foundation. The two become one, a single, more massive anchor for the new, combined galaxy. The irony is that this galactic collision won't bring darkness, it brings light. Those gravitational tides that warp the spiral arms, they do something else. They take these huge, cold clouds of hydrogen gas, drifting out there between the stars, and they slam them together. That gas is the raw material. When the clouds collide, they don't just mix, they compress. They get squeezed by immense pressure, and inside those dense knots, gravity takes over. A clump of gas starts to collapse under its own weight. It spins faster, the core heats up, the temperature and pressure get so extreme that nuclear fusion ignites. And a star is born. Now imagine that process, not in isolated pockets, but everywhere, across the whole tangled mess of two merging galaxies, billions of these stellar nurseries lighting up at once. It becomes a firestorm of creation, a stellar baby boom on an epic scale. The night sky from a planet inside that chaos would be completely transformed. You wouldn't see the familiar, steady band of the Milky Way. The heavens would blaze with the blue-white light of countless newborn stars, vast nebulas glowing in pinks and reds from the radiation of those young suns would paint the cosmos. It would be a celestial fireworks display, lasting for hundreds of millions of years. We don't have to just imagine it, we can see it happening right now in other parts of the universe. The Hubble Space Telescope gave us a preview. It captured two spiral galaxies, the Antennae galaxies, locked in a similar dance. In those images, you don't see neat spirals. You see a tangled wreck of stars being pulled into long tidal tails, the antennae, and speckled throughout that wreckage are thousands of brilliant blue star clusters, each one containing millions of newborn stars. Huge regions of glowing gas mark where the clouds collided and lit up. It's a snapshot, violent, beautiful rebirth. That's the future for the Milky Way and Andromeda. The narrative shifts from doom and collision to spectacular, luminous transformation. This is the life cycle of galaxies written in starlight. They aren't static islands, they grow, they interact, and when they merge, they're reborn in a frenzy of new suns. New solar systems potentially. The old structures get torn down. But from that chaos comes an incredible burst of new light, setting the stage for the next chapter. Our sun, our planet, what happens to them? That's the human question. And the answer is strange but also reassuring. Space is mostly empty. That emptiness protects us. The odds of our sun hitting another star through all those billions of years are incredibly small. The solar system will stay together, the planets will keep orbiting, Earth will keep spinning, but that doesn't mean nothing changes. The real change comes from gravity. A gentle, relentless push. As the galaxies merge, our solar system is like a passenger on a huge ship moving through a slow hurricane. We'll be tugged by the combined pull of billions of stars. Simulations show different paths. We might be swung into a wider orbit around the new galactic center, maybe carried far out into one of the long tidal tails. Or, less likely, the gravity could act like a slingshot. It could be just right to fling our whole system out of the galaxy entirely. We'd become a rogue system. Drifting in the black between galaxies, our night sky would fade. The tapestry of stars would become a near-perfect void, just the faint glow of distant galaxies like islands. Long before any ejection, the sky will change. Over thousands of years, the smudge of Andromeda will grow. It'll become a brilliant, tilted disk of light. Eventually, it will rival our Milky Way, then overwhelm it. The two structures will stretch across the sky. Their spiral arms will warp and blend. Then, during the peak, the sky will ignite. New suns born from colliding gas will blaze to life everywhere, a spectacle of cosmic birth. Nothing like it has ever been seen from Earth. So will Earth survive? Physically, almost certainly, but the world life would know. The constant, familiar star field that guided evolution, that humans have always wondered at, that will be gone. replaced by a new, dynamic, alien sky. Our journey through the merger is a reminder. We're not just on a planet orbiting a star. We're travelers on a star itself, moving through a galaxy that is always changing shape. Our destiny isn't about collisions. It's about a grand, graceful gravitational dance. The most persistent myth is that a galactic collision means instant chaos. We see it in science fiction. Two galaxies approach, stars smash together in a spectacular fireball. It makes for a great visual, but it's a complete misunderstanding of scale. The reality is far less dramatic and, in its own way, far more profound. Take the most common fear. The chance of our sun colliding with another star during this entire multi-billion-year process is almost zero. It's not just unlikely, it's functionally impossible. To understand why, you have to grasp the emptiness. Our galaxy has hundreds of billions of stars. That sounds crowded, but if you shrunk the entire Milky Way down to the size of North America, each star would be about the size of a grain of sand, and the distance between those grains of sand. Over 2,000 miles. Now introduce another entire continent of sand grains, Andromeda, and let them slowly pass through each other. The grains don't hit. They just drift past, their paths gently altered by gravity. That's the merger, a graceful rearrangement, not a demolition derby. Movies take dramatic license. Watching two faint smudges of light slowly warp over billions of years doesn't make for thrilling cinema. They compress time, they ignore scale to create a single, explosive moment. But the real story isn't about destruction, it's about transformation. The violence happens to the diffuse gas clouds that triggers new star birth. The structure of the galaxies gets torn apart and remade. But the stars, the solar systems, they mostly just get a new address in a much bigger city. The slow-motion grandeur of the actual event is more fascinating than any fictional explosion. It's a story of cosmic patience, gravitational choreography, where the universe takes its time to build something new. Knowing the facts doesn't ruin the wonder. It replaces a simple fantasy with a deeper, more astonishing truth. We can be sure about events so far ahead because we have a way to see it. We use supercomputers. If you give them the laws of physics and the data we have now, you can run time forward. You can build a digital version of the galaxy's future and watch it. It begins with all the measurements, the masses of the Milky Way and Andromeda, their speeds right now, their paths, where their stars are, and the dark matter halos. That invisible mass is what really holds the gravity for each galaxy, so that has to be right. All that becomes the starting point for a virtual universe, running on the equations for gravity and motion. Then the simulation runs, not in days but in millions of steps. The computer figures the pull between billions of particles, each one a clump of stars or dark matter. It's a dance done with math. There's a famous project for this, TNG. It doesn't just simulate two galaxies. It models a whole virtual universe from near the Big Bang to now, and it includes mergers like the one we expect. When you watch it, you see the story. Two spiral disks come together. They don't crash head-on. They swing past each other first, their shapes stretching out into long tails of stars thrown into space. They loop back around. Their cores get closer each time until finally they merge into one glowing ellipse, a new galaxy. These aren't just animations. They're tests. Scientists run them again and again, changing the starting conditions. If an idea about dark matter is wrong, the simulation makes a galaxy that doesn't match what we see in reality. So the models get refined against what's real. They show the merger isn't just a possibility. It's the strong, repeated result whenever you put in our numbers. That's how we know it's not a guess, it's a computational destiny. We've watched it happen inside the quiet math of a machine, a front row seat to the deepest future. The stars and gas we see, they aren't the main thing. What's really directing everything is something we can't see, dark matter. It makes up about 85% of all matter. We only know it's there because of gravity. It doesn't shine, it doesn't reflect light, it's completely invisible, but it's the invisible architect of everything in the sky. Every galaxy, ours included, sits inside a huge, diffuse sphere of this dark matter, a halo. So the bright galaxy of stars we see is just the dense core at the center of something much larger. It's like the glowing tip of an iceberg, and the iceberg itself is dark matter. This halo is immense. It stretches far past the visible edge of the galaxy, and it holds most of the galaxy's mass. So when we talk about the Milky Way and Andromeda pulling each other together, it's not stars pulling on stars. It's mainly Andromeda's huge dark matter halo pulling on ours. The stars are just along for the ride. They're like the visible puppets, and the dark matter halos are the ghostly hands moving them. That changes the picture. The merger isn't two spirals colliding. It's two giant spheres of invisible matter already overlapping out there in the dark, pulling their luminous parts into a shared fate. But how do we know this invisible stuff is real? The evidence comes from watching galaxies move. In the 1970s, Vera Rubin studied how spiral galaxies rotate. She expected stars on the outer edges to orbit slower, like Pluto orbits slower than Earth. But her measurements showed something else. Stars on the edges were orbiting just as fast as stars near the center. The only way that could happen is if there was a huge amount of unseen mass out there, beyond the visible stars, providing extra gravity to hold those fast stars in place. That unseen mass is the dark matter halo. More proof comes from gravitational lensing. Einstein said a massive object warps space-time, bending light. When we look at distant galaxies, sometimes their light gets distorted and magnified as it passes through the gravity of a galaxy cluster in front. But the bending we see is too strong to be caused by the visible stars alone. There has to be an enormous amount of invisible mass there warping space. That, again, is dark matter. So as we watch our galaxy's future unfold, it points to this deeper mystery. The fate of every star, every nebula, every possible world is being shaped by something we can't see or touch. The luminous universe is just the visible part of a hidden structure. The two great spirals are gone. What's left is a single, immense galaxy. Astronomers sometimes call it Milkdromeda or Milkomeda. It's not a pinwheel anymore. Its final shape is elliptical. Picture a three-dimensional swarm of stars like a football or a glowing egg. No spiral arms, no distinct disk. The stars inside move on chaotic orbits, buzzing in all directions. Like a stirred-up hive, that's the legacy of the merger. All those close passes, all that tidal pulling, it didn't just warp the old structures, it erased them. It scrambled the orderly, circular motion into a turbulent cloud. The flat disk we live in now will be a memory, and with that new shape comes a new character. Spiral galaxies like ours are often blue, alive. They have gas and dust, fuel for new stars, constant birth. But an elliptical galaxy like Milkdromeda is different. Astronomers call them red and dead. The violent merger used up most of the gas or expelled it. The great starburst fires burned out. Without that raw material, star formation stops. The galaxy quiets. The brightest, bluest stars burn out first. What's left are the older, redder stars. The overall glow shifts from blue-white to a golden red. It becomes a place of aging suns, not newborn ones. A stable, quieter retirement. That's the ultimate destination. For tens of billions of years after the merger, Milkdromeda will stay in this form. A giant elliptical galaxy dominating our local space, a monument to the event that created it. From inside, the night sky would be completely foreign. No band of the Milky Way, no tilted disk of Andromeda, just a uniform, dense sphere of stars in every direction, horizon to horizon, a bright concentration at the core where the two black holes finally merged. It's a sobering conclusion, but also magnificent. Our galactic home, after its long, turbulent history, finds a final, serene identity, not with a bang. With a slow, red glow of countless ancient suns holding their light for eons. But that's not where it ends. You have to pull back. Our two galaxies, they're just the main ones in this small neighborhood. The local group, over 50 galaxies, all held together by gravity, drifting as a single family. And the merger of the Milky Way and Andromeda, that's the big event, but it's not the final one for the group. There's the Triangulum Galaxy, third largest in our group, a spiral you can see with binoculars on a good night. Right now, it orbits Andromeda like a moon. When the two giants merge, Triangulum's fate is uncertain. Simulations show it could get caught in the dance. It might swing by the merging pair, get a gravitational slingshot, flung out on a wide orbit around the new galaxy. Or its path could decay. It might spiral in, merge with Milkdromeda itself, add its stars to the mix billions of years later. It shows you the consolidation is slow. Multi-stage, and Triangulum isn't alone. All the smaller galaxies hear the Magellanic Clouds, the dwarf spheroidals around both the Milky Way and Andromeda. They'll share this fate. Over the next 100 billion years, gravity does its work. Every single galaxy in the group gets drawn to the center. They all merge. The result is one colossal elliptical galaxy. A titan with the combined starlight of our entire local family. That's the ultimate destiny for our corner, total consolidation. But then you zoom out further. To the scale of the whole observable universe, a different story unfolds. Other galaxy groups and clusters are moving away from us and accelerating. That's dark energy, a force in empty space pushing the cosmos apart. Over eons, that acceleration becomes the dominant force on the largest scales. So picture that future. Our local group has merged into one giant island of stars. But outside, the universe has changed. Because of the accelerating expansion, every other galaxy cluster gets carried beyond our cosmic horizon. Their light stops reaching us, they fade from view, then vanish from any detection. Our supergalaxy is utterly alone, adrift in an expanding blackness. From that far future, astronomers, if there are any, would look out and see nothing. Emptiness in all directions. The evidence for the Big Bang, the cosmic microwave background. It redshifts into undetectability. The universe appears static, eternal and empty. All traces of the vibrant cosmos we know gone, except for this one last island of light. So the story becomes one of unity and then profound loneliness. A gathering of all nearby stars into one community, followed by an eternal farewell to everything else. That final island of stars, Milkdromeda, it makes you wonder about life. Could it exist there, not just survive, but thrive through all that chaos and into the long quiet after? The astrobiological puzzle of a galactic merger. You start with a gift. The collision triggers that huge burst of new star formation, and with new stars come new planets. The gas clouds colliding aren't just hydrogen. They're enriched with heavier elements, metals, forged in earlier generations of stars. That metal-rich environment is perfect for rocky planets like Earth. So in the fiery aftermath, countless new solar systems could be born, each one a potential cradle. It's a cosmic reset, creating fresh real estate on a staggering scale. But the same event that builds also destroys. Those brilliant blue newborn stars are massive. They live fast and die young. Their deaths are supernova. Explosions that flood space with intense radiation and high-energy particles. For any fledgling planetary system nearby, that could be a sterilizing event. A wave of radiation scouring away atmospheres and surface chemistry. The galactic core, where star formation is most intense, might become a dangerous neighborhood. Periodically swept by these waves, life would need to arise in the quieter suburbs further out, or be incredibly resilient. Then there's a grander speculation. Imagine a civilization, if one exists, witnessing the approach. They'd have millennia to prepare. Their science would tell them the story long before the skies changed. Could they become interstellar, using that immense span of time to navigate the shifting stellar geography? They might learn to predict the dangerous waves of radiation, or even migrate their species to safer, younger star systems born from the merger itself. The challenge becomes foresight and adaptation on a scale we can barely conceive. It makes you think about life's tenacity. On Earth, we find organisms in extreme places, boiling vents, acidic pools, deep underground. Life, once it takes hold, is stubborn. Could that resilience extend to a galactic scale? Could biospheres persist or even spread through an event that reshapes an entire galaxy? The merger tests the idea of life not as a fragile accident, but as a potential, enduring feature of a dynamic universe. And that connects the astrophysical event back to us. It reframes our place. We're not just passengers on a stable, eternal island. We're inhabitants of a galaxy that's part of a longer story of change and renewal. Our existence here and now, in the relative calm before the storm, might be a special chapter, a window of cosmic quiet, ideal for a civilization to look up, understand its fate, and maybe one day learn to ride the tides of change. The universe has already written the story of our future. It's written in starlight scattered across the cosmos, and we can see it right now with our most powerful eyes. We're watching galaxies collide. The Hubble Space Telescope and now the James Webb, they've given us a front row seat. We're watching the very processes that will one day reshape our own home. These aren't artists' impressions, they're real-time portraits of cosmic transformation. Take the pair known as the mice galaxies. From our vantage, they look like two spirals caught in a tug of war. A gravitational tug of war. Long, graceful streams of stars stretch out behind them. They form these tails that span hundreds of thousands of light years. Tidal tails, they're the direct result of the immense pull each galaxy exerts on the other. That pull flings stars and gas out into intergalactic space. It's a perfect snapshot, a snapshot of the first close pass, the very stage our Milky Way and Andromeda will enter billions of years from now. Then there's NGC 6052. At first glance, it looks like a chaotic mess, a luminous blob, but you look closer, you can still see the two bright cores, the former hearts of two separate galaxies, now orbiting each other inside a shared cloud of stars. A churning cloud, their spiral arms are completely gone, twisted and blended into a single, turbulent structure. This is the merger in progress, a glimpse of the middle act. But the most telling detail in all these images, it isn't the distortion, it's the color. Scattered across the wreckage are these brilliant blue-white knots of light. Superstar clusters, regions where colliding gas clouds have ignited a firestorm of new suns. Each knot can contain millions of newborn stars. They blaze with intense ultraviolet light. That light makes the surrounding nebulas glow in vibrant pinks and reds. The evidence goes beyond pictures. Astronomers use spectroscopy on these colliding systems. They split the light into a rainbow. They look for the fingerprints of specific elements, and in these merging galaxies, they find the signs. The unmistakable signs of rampant star formation. The light is dominated by the signatures of hot, young, massive stars, the kind that live fast and die young. This data confirms what the images suggest. These collisions are not tombs, they're cradles. They are factories of creation operating on a galactic scale. This observational evidence, it's the bedrock of our prediction. We aren't just extrapolating from equations in a vacuum. We are looking at the universe's own laboratory. We're watching the same physical laws play out in distant systems. The processes that will gently pull our sun into a new orbit. The processes that will ignite new constellations in our distant descendant sky. They are the very same processes painting these portraits, these magnificent portraits of chaos and rebirth, billions of light years away. The future of our galaxy is not a unique prophecy, it's a common chapter, a beautiful and violent chapter in the life story of galaxies everywhere. Our star is on a different schedule. The Sun is a middle-aged yellow dwarf. It's been the anchor of our solar system for over 4.5 billion years. Its core fuses hydrogen into helium. That's what gives us light and warmth. That's what made life possible. But that fuel won't last forever. In about 5 billion years, the Sun will start to change. And that timeline lines up almost perfectly with the first great pass of Andromeda. So as the galaxies begin their dance, our star will begin its final act. Deep in its core, the hydrogen will start to run out. The balance will break. The balance between fusion pushing outward and gravity crushing inward. The core will contract, it will heat up, and that new heat will push the Sun's outer layers outward. With immense force, the star will swell. It will transform from a yellow disk into a red giant. Its surface will cool to a ruddy hue, but its size will become monstrous. It will expand past Mercury's orbit, past Venus. It will likely engulf Earth itself. The inner solar system will be inside the atmosphere of a dying star. The planets we know will be gone, vaporized. This expansion phase might last 1 billion years. But it's not stable. Eventually, those swollen outer layers, loosely held by gravity, will drift away. They'll be cast off into space, forming a glowing shell of gas. A planetary nebula. That nebula will expand and fade over thousands of years, its material returning to the galactic reservoir. And all that will remain of our Sun is its hot, dense core. A white dwarf, an Earth-sized ember of carbon and oxygen, shining with leftover heat. It will take trillions of years to cool completely into a cold, dark crystal. So you have these two clocks ticking in the vastness. One is galactic. It measures the slow-motion merger of two families of stars, a story of chaos and creation and new structure. The other is stellar. It measures the quiet transformation of a single, ordinary star and its planets, a story of consumption and loss and a gentle fading. They're both true. They're both happening in the same stretch of cosmic time. This contrast is poignant. It shows the universe operates on many scales at once. A galaxy can be reborn in fire and light, while within it, 1 million individual suns are following their own paths toward their own ends. Our solar system story will conclude long before the galactic merger is complete. We're living in a brief, golden age of stability, nestled between these two great arcs of change. The final hum from those merging black holes would be something we've never heard before. The collisions LIGO picked up, those were from stellar mass black holes, each maybe a few dozen times the mass of our Sun. Their merger is this high-pitched, rapid chirp in space-time, over in less than a second. But the dance at the center of our galaxy, that's on a completely different scale. These are supermassive black holes, millions of times heavier. Their orbital waltz takes years, not fractions of a second. The gravitational waves they make aren't a quick snap. They're a deep, resonant thrum, a bass note so low that a single wave could take years, even decades, to pass by us. That frequency is far below what ground-based detectors like LIGO can sense. Their instruments are built for the cosmic shrieks, not the cosmic groans. To listen for this, we have to go to space. A future mission called LISA, the Laser Interferometer Space Antenna, is being designed for exactly that. Picture 3 spacecraft flying in a perfect triangle millions of miles apart, linked by laser beams. They'd form the most sensitive ruler ever built, just floating in the quiet of the solar system. When a gravitational wave passes through, it would minutely change the distance between the spacecraft, stretching and squeezing space itself. The lasers would catch that microscopic wiggle. Lisa would be an ear tuned to the low-frequency symphony of the universe, listening for the mergers of supermassive black holes across cosmic time. If we could speed up those waves and turn them into sound, the merger of our galactic cores wouldn't be a crash. It would be a deep chirp, rising in pitch and volume over millions of years as the black holes spiral closer, ending in a final, profound tone when they become one. It's the sound of space-time itself ringing like a bell, and this isn't just theoretical. It's the next frontier of astronomy. For centuries, we've studied the universe by collecting light from radio waves to gamma rays. Gravitational wave astronomy lets us listen to it. We're moving from being silent observers of a cosmic movie to having a full surround sound experience, sensing the universe through the vibrations of its very geometry. The inevitable collision of our galaxy gives us a specific, distant event to listen for, a predicted note in that future symphony, showing that even the grandest transformations leave an echo in the fabric of reality. From a world in the middle of it, the sky would turn into a living canvas. The first change would be slow, taking thousands of human generations. That faint smudge in Andromeda, that fuzzy patch of light, it would start to swell. Over years, over centuries, it gets brighter, it gets larger, its real shape starts to come clear. It's not a smudge anymore, it's a distinct, glowing ellipse tilted there against the stars. In a few million years, it dominates everything, a second great river of stars matching our own Milky Way, then passing it. The night is split in two by these colossal arches of light intersecting. Then the real show starts. The galaxies make their first close pass, and gravity goes to work. The orderly spiral arms of both galaxies, those graceful curves, they begin to distort. You'd see them stretch like taffy pulled across space, long streams of stars' tidal tails flung out, arcing away from the main bodies like brushstrokes. The sky doesn't have two separate shapes anymore. It becomes a tangled, brilliant web. A web of starlight with knots of intense blue where new star clusters ignite. Andromeda's core blazes as a second hub right beside our own. At the closest approach, the view is almost too much. From a well-placed planet, you might see Andromeda's warped disk covering a third of the sky, its spiral structure visibly shredded, mingling with the tattered remains of the Milky Way's arms. The dark lanes of dust from both galaxies weave complex, shadowy patterns against all that light. It's a dynamic tapestry, three-dimensional, changing noticeably in a single lifetime. New stars, born from the colliding gas, flash into existence as brilliant blue-white points, outshining everything else for a while. Artists and scientists with supercomputer simulations have tried to picture this future sky. The images show something we've never seen, not a static dome of pinpricks but a deep, layered, active panorama. You'd feel inside the event, not just watching from afar. The depth would be profound, some stars sharp and close, the merged galactic cores a diffuse, combined haze in the distance. For any civilization there, astronomy wouldn't be the study of distant, unchanging objects. It would be recording a real-time cataclysm of beauty, a spectacle written across the heavens, the ultimate reward for a conscious observer, a front-row seat to cosmic rebirth, watching the old constellations dissolve and new patterns form in the slow-motion fire of creation. The galactic roadmap we know would be gone. For a long time, civilizations have used the constellations, the steady band of the Milky Way, but in Milkdromeda, that fixed map disappears. The spiral arms are gone, those great highways are gone. What you have instead is a three-dimensional swarm, stars moving in every direction on random orbits. Like a hive that's been stirred, you couldn't just look up and see a bright band and know where you are. Ideas like galactic north or the plane of the ecliptic, they lose their meaning here. You'd need new methods. One idea is absolute beacons. The merged black hole at the core would be a fixed point, a brilliant radio source, a central lighthouse. Then you have pulsar networks, those spinning neutron stars that tick with perfect rhythm. They could act as a cosmic GPS. Their unique pulse signatures would let a ship triangulate its position in all that chaos. Navigate by dead reckoning through the stellar cloud. It's a huge challenge. You have to shift from thinking in 2 dimensions to full 3-dimensional awareness. But within that challenge, there's an opportunity. The merger doesn't just scatter stars at random. It mixes 2 whole populations, star systems that once belonged to separate galaxies, separated by millions of light years. They get thrown into the same gravitational pot. Their orbits intertwine, distant suns are brought closer together. In certain regions, the average distance between stars might actually decrease. For interstellar travel, that changes everything. The vast, empty gulfs between spiral arms are gone. In the core of Milkdromeda, the stellar density is much higher. A journey that once meant crossing a lonely desert might become a shorter hop. Between more closely packed stars, it reimagines the galaxy not as a vast, lonely frontier, but as a bustling metropolis, a connected metropolis of suns. This vision blends astrophysics with exploration. It asks about adaptability on a cosmic scale. If life persists through the merger, its greatest achievement might not be just surviving. It might be learning to sail the new tides, to turn that stellar chaos into a navigable sea. The galactic future isn't an ending, it's part of something older. A much grander process, one that built the universe we see. That process is hierarchical assembly. It's the cosmic rule. Small things merge to make bigger things. Over billions of years, tiny clumps of dark matter and gas drew together. They formed the first small galaxies, irregular ones, and then, drawn by gravity, those small galaxies began to merge. They combined their stars, their gas, their dark matter halos. They built larger structures, the majestic spirals we see, the giant ellipticals. They weren't born that way. They were assembled piece by piece through mergers. Our own Milky Way is a testament to that. It's not a pristine island, it's an archive of past collisions. Astronomers map the motions of stars, their chemical compositions, and they find ghosts of smaller galaxies, our own, consumed long ago. One of the most famous is Gaia Enceladus. A dwarf galaxy, it collided with the young Milky Way maybe 10 billion years ago. Its stars were scattered throughout our galactic halo. Their distinct chemical signature tells that story. That ancient merger, another is the Sagittarius dwarf spheroidal galaxy. We're absorbing it right now. Its stars are being pulled into long streams that wrap around our galaxy. So the Milky Way we call home is already a hybrid, a product of this relentless, constructive violence. The collision with Andromeda isn't our first merger. It's simply our next and our largest. These mergers do more than add stars. They're engines of galactic evolution. When gas-rich galaxies collide, the chaos does something crucial. It funnels vast reservoirs of cold gas toward the galactic center. That's like sending fuel to a furnace. The furnace is the supermassive black hole. As this gas spirals in, it forms a hot, bright disk. An accretion disk. Friction and magnetic forces heat it to incredible temperatures. It glows across the spectrum. For a time, the galactic core can outshine all the stars in the galaxy combined. We call that brilliant beacon a quasar. It's the most powerful type of active galactic nucleus. A quasar isn't permanent. It's a phase, triggered by a merger that delivers a feast of gas to the central black hole. This process creates a feedback loop. It shapes the galaxy itself. The intense radiation, the powerful jets from the quasar, they can blow away the remaining gas, quenching further star formation. It's a self-regulating mechanism. The merger provides the fuel for a brilliant, temporary fire, and that fire then helps determine the galaxy's future character. Whether it remains a star-forming spiral or settles into a quiet, red elliptical, So when we look ahead to Milkdromeda, we're not looking at a freak event. We're watching a standard procedure, a universal procedure, a procedure that built the cosmic structures around us. Our local story is a single example. A vivid example of the process that assembled the entire cosmos, from the first tiny galaxies to the great clusters we see today, that elevates the narrative. From a tale of two galaxies to a recognition of our place in an ongoing saga, a dynamic saga of construction, the models show us a future. A clear picture, but they also show where the picture gets blurry, where the science points to its own edges. We know the merger will happen, that's certain. But the precise choreography, the dance itself, still has mysteries. One of the biggest is tangential motion. We know Andromeda is moving toward us, but its sideways motion across our line of sight, we don't know that with perfect precision. Is it coming straight in, or does it have a glide, a sideways component? That slight component changes everything about the first passes. It determines whether the galaxies swing by in an arc or whether they engage in a series of loops. A more drawn-out series. Our measurements from Gaia have refined this, but a tiny uncertainty remains, so the exact sequence over the next few billion years has a few possible scripts. Then there's the physics of the gas. In simulations, we treat it as a fluid, gravity and pressure, but real galaxies have magnetic fields threaded with them. Invisible lines of force, and those fields can influence the gas clouds when they collide. They can provide extra support, slow collapse, channel flows in unexpected ways. Simulating that perfectly across an entire galaxy is a monumental challenge. The same goes for the details inside each giant molecular cloud, that turbulent, chaotic detail. Those small-scale complexities can affect the timing, the intensity of the great starbursts, the fireworks that will define the merger's middle act, and then there's the potential for surprise. That might be the most intriguing unknown. We're talking about two of the most complex systems in nature interacting, each with hundreds of billions of stars. Vast gas clouds, dark matter halos, active black holes. When systems of that complexity interact, they can show emergent behaviors, phenomena that are hard to predict from the individual parts. Could the merger trigger activity in the galactic cores that defies our expectations? Could the mixing of two stellar populations yield unexpected star clusters? New types. The history of astronomy teaches us that whenever we look with new tools, we find phenomena we never imagined. This isn't a weakness in the science. It's its strength. The story of the collision isn't a finished book. It's a living document, updated with new data from telescopes, more powerful simulations. The core prediction of the merger is solid as anything, but the glorious details, the intricate details of how it will unfold, are still being written. That space for the unknown, for future discovery, is what keeps the wonder alive. It means when we peer billions of years ahead, we're not just reading a predetermined fate. We're following a trail of evidence, a trail that promises new revelations at every turn. The cosmos always has one more secret to share. We're faced with time itself. We build monuments, we write histories, we try to leave something that lasts thousands of years, but all of that happens inside a human lifetime, and the universe works on a scale where thousands of years are just brushstrokes. The life of a galaxy is one slow scene in a much longer play. We want permanence, we look for things that are eternal, but Milkdromeda shows something else. On the largest scale, change is the only thing that stays. Spiral galaxies don't last forever. The constellations we know aren't fixed. Even the night sky, that old, reliable map, is temporary. That view can be unsettling. It's humbling. It puts the whole human story inside a frame so large it seems to shrink it. Carl Sagan talked about this. He was reflecting on the pale blue dot photo, Earth seen from the edge of the solar system. From there, our planet is a speck of light, a tiny point in a sunbeam. All of human history happened on that pixel. Every war, every piece of art, every love. He said that in that cosmic setting, our posturing, our self-importance is challenged by that pale light. Our world is a lonely speck in a vast dark, but there's another side to that humility. If nothing is permanent, then everything is precious. The fact that we're here at all, conscious during this stable window, is a kind of miracle. We exist in a golden age for looking, after the mergers that built our galaxy and before the next one that will change it. We get to look up to understand our place in this story, to feel the awe that comes with that, and that changes the question of legacy. It shifts from building something that lasts forever, which the cosmos says is impossible, to creating meaning in the time we have, to adding our note, however short, to the symphony of discovery. What does our striving mean if even galaxies are temporary? Maybe it means meaning isn't about outlasting the universe. It's about understanding our part in it, our science, our art, our stories. That's how we map our brief light against the dark, how we connect our human time to the deep time of stars. The collision reminds us we're not separate from the cosmic dance. We're made of stardust from events just like it. We're riding a star that will one day be part of a new galaxy. So our search for meaning becomes part of the universe's own story, a fleeting moment of awareness in the long, patient night. Galactic mergers aren't rare. They're the rule. To see how common, you look back, way back, when the universe was young and dense and chaotic. In those first few billion years, galaxies were packed close. Space was smaller, the expansion hadn't stretched things out yet. In that crowded early cosmos, collisions were happening everywhere, all the time. It was how galaxies grew. Small proto-galaxies, irregular blobs smashing together, building up into larger structures. That era was the great age of assembly, a frenetic period of construction. It laid the foundation for the spirals and ellipticals we see now. We know this because our most powerful telescopes are time machines. The James Webb Space Telescope, with its infrared eyes, looks into that deep past. Light travels at a fixed speed. Look at a galaxy a billion light-years away. You see it as it was a billion years ago. Webb looks at galaxies so distant, their light has been traveling for over 13 billion years. We see them as infants, and in those infant galaxies, Webb is finding something. It's finding pairs, it's finding tangles, systems clearly in the process of merging. Long before they settled into stable shapes, these aren't the clean spirals of today. They're messy and clumpy and violent. Brilliant knots of star formation ignite where gas clouds collide. The images show galactic car crashes frozen in time, from an epoch when this was everyday. That changes our perspective on the Milky Way and Andromeda. Our impending merger isn't some special, catastrophic destiny. It's a late example, a final, major chapter in a story mostly written long ago. The great age of mergers peaked billions of years in the past. Since then, the universe has expanded. Galaxies have been carried farther apart. Major mergers between giants like ours have become rarer. We're living in the relatively quiet aftermath of that early frenzy. So when we project forward, we see our galaxy participating in one of the last great acts of consolidation in our local group. It's a closing echo of the process that built the cosmos. That context is everything. It links the local fate of our sun, our night sky, to the grand narrative of the universe's evolution. Our future becomes a single, vivid day to point in the long history of galactic growth. A reminder the cosmos isn't a static painting. It's a dynamic, unfolding story, and we're here to witness a pivotal, though patient, turn of the page. The sun's hold on its planets is surprisingly strong. Even when galaxies collide, that bond is different. It's a much more local kind of force. Think about the gravity you feel right now. Earth pulls you down, that's your weight. The sun pulls on you too, but from 93 million miles away, that pull is more than 1,000 times weaker. Then there's the whole galaxy, all that mass spread over 100,000 light-years. It's just a gentle background pull, but the sun's gravity that dominates our solar system completely. It's like the difference between the tide coming in on a beach and water swirling down a drain. One is a slow, vast heave, the other is an immediate, tight vortex. A galactic merger will change that background tide, but it won't break the vortex. We can measure this. The tidal force from another galaxy is a difference in pull, the galaxy tugging a little harder on one side of the solar system than the other. For something as close as Earth, that difference is tiny. The sun's hold on Earth is about 30 million times stronger than the strongest tidal force Andromeda could ever exert. The planets aren't marbles about to roll off a table. They're glued in place, their orbits set almost entirely by the sun's gravity. That stability isn't a guess. It comes from the emptiness of space, and the inverse square law gravity weakens dramatically with distance. But at the very edge of the sun's influence, things get more subtle. That's the Oort cloud, a hypothetical shell of icy bodies starting almost a light year out. There, the sun's grip is weak. An object out there orbits so slowly one trip can take millions of years. It hangs in a delicate balance. For these distant objects, the changing galactic tide isn't a small ripple. It's a real, persistent nudge. Over the eons of a merger, as the background gravity shifts, some of these icy bodies could have their orbits disturbed. A gentle push inward, a new path that sends them falling over thousands of years into the inner solar system as long-period comets. So the answer is layered. The inner planets, from Mercury to Neptune, their clockwork will keep ticking with near-perfect reliability. Their orbits are etched in stone, but the solar system's outer frontier, that silent reservoir of ancient ice, might experience a slow-motion stir. The galactic merger could, over billions of years, slightly increase how often these icy visitors arrive. It's a reminder that even in cosmic stability, there are degrees. Our home world is secure, but the depths where comets come from, they are connected to the grand dance of the galaxies. We know what happens to the giants. But they aren't alone. The Milky Way has satellites. Andromeda has satellites. Ours, the most visible, are the Magellanic Clouds, those two glowing patches you see from the south. For Andromeda, its main companion is the Triangulum Galaxy, a spiral itself, and then dozens of smaller dwarfs, all of them orbiting, bound. These orbits are slow, wide, taking billions of years, but when the merger starts, that order breaks. The gravity between the two giants creates huge tides. For the small galaxies in the middle, it's like being in a room with two swinging magnets. Their stable paths get shaken. Some are flung outward, maybe even ejected from the local group entirely, sent into the void. Others spiral inward toward the turbulent center. But in all cases, their structure can't hold. These dwarfs are held together by their own weaker gravity. As they're pulled, they experience tidal stripping. The stars and gas on their outer edges feel a stronger pull from the hosts. They get peeled away, drawn out into long streams, faint ribbons of starlight. They slowly disperse, joining the halo of the new galaxy. Simulations show these streams, ghostly arcs, marking the dissolution. The core of the satellite might hold together for a while. A denser knot, traveling with its own trail of lost stars, but eventually it too gets assimilated, its identity erased, its stars scattered, mixed with stars from both major galaxies and all the other absorbed companions. So this adds a layer. The merger isn't a clean, two-body problem. It's the messy consolidation of an entire galactic family. Every member contributes. From the great spirals down to the faintest dwarf, all their stars, their gas, their history goes into the final form of Milkdromeda. The new galaxy's halo becomes an archaeological site. Its stars bearing chemical signatures from many origins, a testament to the dozens of smaller galaxies that were consumed. The grand collision is really a unification. gathering every island of light in our local corner into one last great community. You can see it in other galaxies. The evidence is out there. Our merger isn't something special. It's how galaxies grow. Most of the big galaxies we see, especially the smooth, football-shaped ones in clusters, they were built by mergers. That's how they got that way. Even spirals like ours, they have scars, streams of stars from things they've eaten. This is the normal story. It's how things are assembled, and we can watch it happening. In Virgo, there are two spirals, NGC 4567 and NGC 4568. They're starting to overlap. Their arms are warping. Gravity is pulling out these long filaments of gas and stars between them. It's a snapshot, a preview of our own first close pass, but happening far away. It shows our future isn't unique. It's a common chapter that changes how you see our neighborhood. Our local group, with its few dozen galaxies, it's a quiet suburb, a backwater. Compare it to the Virgo cluster, over 1,000 galaxies. Their mergers are constant. Galaxies whip past each other, shapes get distorted. The space between them is filled with hot gas stripped away during these interactions. It's perpetual chaos. Living here is like a peaceful town. Virgo is a frenetic city. Seeing our future this way, it doesn't make it smaller. It normalizes it. It puts Milkdromeda right inside the standard story. The universe isn't a static museum. It's a construction site. Gravity is the builder, pulling things together into new designs, from the frantic early mergers to the slower ones now, like ours. Change is the engine. Our quiet suburb is just having its turn, on a schedule written by the same forces that govern everything, that connects our local fate to the grand process. It means we're watching a universe that's always in motion, at every scale. Milkdromeda ends up as a giant, smooth ellipse, a huge three-dimensional cloud of stars. There's no flat disk anymore, no spiral arms. The stars inside, they don't move in neat circles like cars on a track. They buzz in every direction, chaotic, tilted paths. It's like a stirred-up beehive. That's the trait of an elliptical galaxy. Order gives way to a kind of organized chaos. Gravity holds it together, but there's no single plane of rotation. The pinwheel structure we had is gone. Without that disk, something crucial is missing. The thin, rotating plane of a spiral. That's where the magic happens. That's where the cold gas and dust can settle, collapse, ignite new stars. In this elliptical swarm, that organized reservoir is absent. The Great Collision used up most of the gas in furious bursts of creation. What wasn't turned into stars got blown away by radiation or heated too much to collapse again. So the era of prolific star birth is over. Milkdromeda enters a long, quiet autumn. Its stellar population ages together. The massive, hot blue stars, the ones that light up spiral arms, they burn through their fuel in just millions of years. They're the first to go in supernova. What remains are the longer-lived stars like our Sun and the countless smaller, cooler red dwarfs. Red dwarfs can shine for trillions of years. The galaxy's overall glow shifts from blue-white to a warmer, golden red. Astronomers often call galaxies like that red and dead, not because they're lifeless, but because their period of star-forming vitality has passed. In terms of sheer scale, this new entity is a titan. It contains the combined mass of perhaps over 1 trillion stars from both galaxies, plus all the smaller ones consumed along the way. It utterly dominates our local group. For hundreds of billions of years, it'll be the central island of light in an otherwise expanding dark sea. From within, the night sky would be profoundly different. You wouldn't see a band of light splitting the heavens. Instead, the sky would be thick with stars in all directions, a bright, concentrated glow toward the core where the merged black hole resides. It's a stable, enduring form, a monument to the merger that created it. But if you remember the elegant architecture of spirals, their stellar nurseries, their sweeping lanes, this new home might feel less picturesque. A grand but static cathedral compared to the dynamic, living river of stars we once called home. The timescales here, they push against this basic human need to leave something behind. So if we, or whatever comes after us, wanted to send a message across that whole merger event, you have to ask if anything could make it. The physics of the collision, it gives you the constraints. It sets the rules. First problem is where you put it. Our solar system, it's going to be relocated. It'll be a gentle process, but the change is total. We could end up in a tidal stream or thrown way out from the galactic center. So any beacon you anchor to a planet or even to the sun, it goes with it. Its location in the galaxy, that address, it becomes completely different. A message for the deep future. It wouldn't need coordinates to a fixed spot. It would need a map to a moving one, a chart of billions of years of drift. Then there's erosion. Over billions of years, everything wears down. Micrometeorites, radiation, atomic decay, it's like a slow, universal sandblasting. A plaque on a world gets buried by geology or worn smooth. A satellite in orbit gets pummeled by particles. Any physical object, the kind we think of, it seems fated to just fade. So you have to shift the idea. Maybe the message isn't an object, it's a pattern. Information encoded not in matter, but in motion. You could take a set of inert, tough bodies, asteroids, small moons, and set them into a precise, resonant dance around a stable red dwarf star. Their positions, their orbital timings, they could spell out a sequence, a number, an image. The gravitational system itself becomes the storage, maintained by physics. Readable by anyone who understands orbits. There's another idea, a lonelier one. The rogue planet, kicked loose from its star during the merger's chaos, drifting forever in the dark between galaxies. A world with a frozen, dead surface. There, in that deep, cold tomb, a record might persist, but the chance of anyone ever finding it, the search space, is just unimaginable. This whole line of thinking, it mixes astrophysics with archaeology, with philosophy. It makes you ask what lasting really means. If even galaxies are temporary, then maybe the only thing that can cross such an age is to join the process itself. To make sure life, or what it learns, isn't just a single, fragile light, but a spark that can jump. To design a message that isn't a monument, it's a seed. Something that can survive the stellar winds and then grow in the new ground of Milkdromeda. The merger is spectacular, but it's just one chapter. Milkdromeda's life will stretch trillions of years beyond that, a future so vast the collision feels like a flash. In this new elliptical galaxy, the great starburst fires burn out. The last cold gas gets used up or expelled. Star formation sputters, then stops. The galaxy shifts from a place of birth to a place of long, slow aging. The brilliant blue stars, the ones lighting up nebulae, have short lives. They go first, exploding or collapsing quietly. What's left are the longer-lived stars like our Sun and the countless faint red dwarfs. These smaller stars are miserly with their fuel. They burn for trillions of years. The galaxy's glow dims and reddens. It transitions from a blue-white youth to a deep, golden red autumn. At the very center, the supermassive black hole, now a single entity from the merger of the two cores, enters a long quiet. It consumed the gas funneled to it during the collision. Now it sits dormant, a dark, massive anchor in a slowly dimming sea of stars. Occasionally, a stray star or gas cloud might wander too close, creating a brief flare. But for eons, it's a silent monument. We can follow the physics further into more theoretical realms, but still grounded in particle physics and cosmology. Over hundreds of trillions of years, the longest-lived stars finally exhaust their fuel. The red dwarfs cool and darken, becoming black dwarfs cold, crystallized spheres of carbon and oxygen drifting in the dark. The galaxy is no longer lit by fusion. Its light comes only from the rare, slow-motion collision of these dead stars, or the faint Hawking radiation of evaporating black holes, a process that takes timescales we can scarcely write down. This leads to a profound, almost philosophical frontier. Some theories suggest the very protons that make up all matter aren't perfectly stable. Over timescales so long they make 1,000,000,000,000 years seem brief, protons themselves might decay. If that's true, then even the cold remnants of stars and planets would, over an almost infinite future, gradually dissolve into subatomic particles and light. The galaxy fades from a collection of solid objects into a thin haze of fundamental particles. Through all this, the black holes are the last structures standing. They slowly evaporate via Hawking radiation, a trickle of energy that, over incomprehensible eons, causes even these titans to fade away. The universe enters an era of profound stillness and darkness, a state of near equilibrium where the energy is spread so thin that almost nothing happens. This vision is somber. It's a logical extrapolation of the laws we know. It provides a startling epilogue to the dynamic, violent story of the galactic collision. Yet, even in this ultimate quiet, there's a kind of grandeur. It completes a cycle that began with the furious energy of the Big Bang, passed through an age of structure and light, and concludes in a vast, serene dark. It reminds us that change is the true constant, from the frantic assembly of galaxies to their final, patient fade into the cosmic background. Our story, from the first gravitational pull to this distant twilight, is a single, coherent arc written across the lifespan of the cosmos itself. The collision is a story for a future we'll never see, but it's not a story without us, and it matters right now because it changes what home means. We're not just living on a planet, we're citizens of a galaxy, passengers on a star that's part of a larger, evolving structure. Knowing its fate connects us to the cosmos. It turns the night sky from a static backdrop into a living page, a story we're starting to read. This is more than astrophysics, it's about perspective. When you grasp a timeline of billions of years, your own scale shifts. The daily worries, the fleeting conflicts, they don't disappear, but they get a new context. They're set against a canvas of cosmic patience that can be a source of humility and also resilience. It shows that change, even catastrophic change, isn't an ending. It's a transformation. The universe is built through transformations. Our own lives are full of endings and beginnings. The galactic story mirrors that. On an epic scale, teaching us about endurance and renewal, this pursuit of knowledge looking billions of years ahead, it's a human endeavor. No other species builds telescopes to map galaxies. No other creature runs simulations to foretell the destiny of stars. We do this not for survival today. We do it because we're driven to understand our context. To answer where we came from and where we're going, that curiosity is our legacy. It pushes technology. It inspires new scientists. It reminds us we're part of something vastly larger. The value is in the looking, in turning our gaze upward, piecing together this narrative from starlight and math. It's a story of connection. The iron in your blood, the calcium in your bones, forged in a star that died long ago. Likely in another galaxy, we are literally made from the remnants of earlier cosmic events. The future merger is just the next step in that cycle of creation and dispersal. We're not separate from the process, we're its product, and we're here to witness it. So why care about an event 4.5 billion years away? Because in tracing that arc, we find our place in it. We see our brief moment of consciousness happens during a rare window, a stable time, a golden age for observation. We get to be the universe understanding itself. That search for meaning, that drive to map our cosmic address, that's what makes this distant future relevant to our human present. It turns the inevitability of change into a source of awe. and our quest to understand it into a celebration of our place in the grand story. We started with our own galaxy, the spiral we live in, and we ended up looking at that red giant out there. And the whole story is really about gravity and about stardust. This motion of the universe, it's slow, it's huge. We're not just watching it, we're inside it, being moved along. The science shows us that. The gravity measurements from 100 years back, the dark matter we can't see but that holds everything together, the gas clouds colliding and making new stars. It all points to a cosmos that's active, that's making things, that's all connected. These aren't just separate pieces of information, they're all part of the same story. A story about things changing. The time it takes is hard to grasp. 4.5 billion years. That's not just a figure, that's the whole life of our planet right there. Trying to really think about that, it forces a different kind of perspective. It goes against our wish for things to last, for things to be permanent. But there's something in that. If nothing is made to last forever, then what we have is valuable. Our time here, this short period where we're conscious, in this quiet stretch between much bigger events, it's a kind of gift. We're here at a good time for seeing, for learning, for feeling that wonder. So this tale about galaxies merging, about rebirth, it's really about how you see things. It shows us that change, even the most destructive kind, isn't a full stop. It's a shift, a violent, bright, slow shift into something else. The spiral becomes an ellipse. New stars fade into a long, red glow. That rhythm of things ending and beginning again, you see it everywhere in nature. You feel it in your own life. It's about coming back, starting over, and our need to chart this future, to understand a fate we'll never see. That's something only people do. It ties the iron in our blood, which came from a star that died long ago, to the new stars lighting up right now in places like the Antennae. We're not just along for the ride, we're the universe in a way starting to know itself, putting its own history together from little bits of light and from the patterns in the math. That need to find meaning, to see where we fit in the story, that might be what we leave behind. So this shouldn't be a conclusion. Think of it as an opening. A reason to keep watching the sky, to not see it as a fixed roof but as a page that's still being written. Andromeda, that faint patch, it's not just another galaxy. It's a sign of what's coming, a sign that we belong to something enormous and beautiful and never still.